morning year 12, time for a bit more redox. Title up there, half equations to redox reactions. Now what we're saying here in this video is understanding half equations, not a lot to understand about those, and how to put them together and you end up with balanced redox reactions. Get straight about half equations first. Half equations, firstly, two things. We'll bullet point them. There we are. Have electrons. So when you have an equation with electrons in it, it will be a half equation. A balanced full equation, no electrons will be seen. They're kind of there, but they're on both sides and they cancel out, so therefore you don't see them. And also, in determining what we're about to do, the old idea of oil rig comes to mind. Two written there. There's a reduction of Mg2+. It's quite difficult to achieve, but nevertheless it is a reduction. The gaining of electrons by magnesium. So oil rig, reduction is gaining, is what's going on there. That's an oxidation of zinc, where zinc is offloading 2 electrons. It's losing electrons, oxidation is losing, hence the oil rig thing. And so those are an example of what reduction and oxidation would look like in very simplistic half equations. So if you've got electrons on the left, it will be a reduction. If you've got electrons on the right, it will be oxidation. Now, if they're both on the left, you can't combine them. If they're both on the right, you can't combine them. We'll come to that later. So there is a thing to be beware of, and that is the type of half equation where they go something minus 2 electrons. So something like 2Br minus 2 electrons. Not good, because that messes with this, because got to be plus for this ruled sort of thing to work. So if the electrons are on the left, it will be plus electrons, so you'll be adding electrons on the left and you'll be adding electrons on the right. Yeah, that makes them that. So beware of the minus electron thing. I have to say, don't often see them like that, but some people still do it. I wag my finger at such people. Right, we're just doing a couple more examples just to show you a couple of things, and then we'll get on to the second part, which is turning them into redox reactions. But I need to get the board ready, so I will see you in a moment. So a couple more examples. The top one a little bit more complicated. So this is manganate 7 technically, and it combines with some hydrogen ions, takes 5 electrons and it turns it into these products. So electrons on the left hand side means it will be a reduction. You can do that with oxidation numbers as well, because oxidation numbers are intrinsically tied to electrons. So if you work out the oxidation number of that, and if you want to check that, pause the video and just check the oxidation number. It's gone from 7 to 2, so it's dropped by 5, which is a reduction. It's 5, so it's gone down by 5. That's why there's 5 electrons in the half equation, because they are exactly the same thing. Here's a much simpler one, and an iodide, well, 2 iodides, offloading 2 electrons, forming iodine. Oxidation. Now I've also written in here something that ties into the previous video. Manganate there, manganate 7, there's a reduction going on, so that means it will have been taking part in a reaction as an oxidant. And similarly, because the iodide has been oxidised, it would have taken part in a full reaction, that is. as a reductant. Now we're going to get on to combining them to make whole equations, but obviously I need to get the board ready for that, so I'll see you after I've done that. So let's do some combining of a pair of half equations. So it has to be a redox pair, meaning one has to be reduction, one has to be oxidation. So if you got given those two, you can't do it. You certainly can't do it like that, because you can't just add them together. What you need is for one of them to have electrons on the right hand side and the other one have them on the left hand side. Now reactivity unlocks what I should have done, because zinc is more reactive than copper, so therefore zinc will displacement reaction. Zinc will displace the copper out of solution. So the copper will do that, because that is copper solid being displaced, and the copper comes out of solution. And so I've got them here the correct way round. So copper gets displaced out of solution, but the zinc metal turns into zinc 2+ ions to push the copper out. Why that works: zinc releases 2 electrons, copper accepts those 2 electrons. So one of the key things you have to have when you're combining half equations, I may have walked out of camera shot there, is that you have the same number of electrons on the right as you do on the left, which I do because there's 2 in each. Obviously that's not going to be quite so straightforward when they're not both got the same number. But these have both got 2 in, so you literally just combine them. The electrons disappear because you have the same number of electrons on both sides, so they cancel out. And there's the combination. Driven by the fact that zinc is more reactive than copper. So you know, with zinc being more reactive than copper, zinc is going to be oxidised and the copper is going to be reduced. As it stands, those 2 there are both reductions. Yeah? So reduction is gaining of electrons, you see. But you need to flip one round so that it goes in the oxidative direction. Now the art of knowing which one to flick round the other way is driven by reactivity, but it's also driven by, at A level, things called electropotentials, year 13, not something we're going to do here. So here we're going to go with just, we've got half equations that are the correct way round to be combined. So that will keep it more simple, and so we don't have to get involved in deciding which one will have to go in, which one has to go oxidation direction, which one has to go reduction direction. So I'm going to do another example, and well, I'll see you when I'm ready. So here's another example, not terribly complicated. Oxidation of magnesium, reduction of silver ions. Got to be that way round. Magnesium is more reactive than silver, so magnesium will displace silver out of solution. So the magnesium will be oxidised into Mg2+, and the silver will be forced to accept the electrons and turn itself into silver. You would see that in a displacement reaction in a test tube. Now, not quite as straightforward as the other one, because 2 electrons, single electron. So the way you have to do this to get them to be the same, you have to go same number of electrons on the left and right. This whole thing needs doubling. Now we've got 2 electrons and 2 electrons. So the electrons will disappear, they will cancel out, and you will go with a combination of the 2 half equations. I'm putting state symbols in because we need to do that kind of thing. Never forget to do state symbols. So it looks like that. But sometimes people say to me, does it matter which order you put these things in? To me, I have no idea whether the order matters. I just go with whatever order I write. I don't think an example would might be wrong, so I wouldn't fuss about it. So there's combining slightly different numbers. We're going to do a more complicated example. I'll see you in a moment. So, more complicated than before. It's this one with the manganate that we had as an example a little while back, and this time we've got iron 2 turning into iron 3. So this is an oxidation, this is a reduction, therefore you've got the correct pair. You can tell that because you've got electrons on the left and then electrons on the right. Combining the two, going to have to be the same number of electrons. This whole Fe one is going to have to go 5 times, because that will then release 5 electrons for this here to need the 5 electrons to take them in. Oh, there's some kind of incident outside with flashing lights. And when you then combine those, you get, quite simply, the two things added together. I'm going to leave the state symbols out because it will save time in me writing. My waters didn't go very well at the end, but you know what it is. It's those there. So combining it, you get that. Now this equation features quite a lot in A level. You see it quite often in exams. So it is one worth really remembering rather than putting it together like this. So it's manganate 7 and 5 Fe2 plus, and the products are there. On the other hand, you don't need to remember it. The question will allow you to work it out or get it depending on the way the question is. But that's a balanced redox equation. It's an ionic equation, obviously, and what you should do is, having done the balancing of the electrons, you should check that you haven't made any other mistakes. So you should count up how many things there are, and there's 1 manganese, there's 8 hydrogens, there's 4 oxygens, you just do the standard check thing. Also, the charge should be balanced, so the total charge on each side. So that is 10, 18, 17 pluses, and there should be 17 pluses over here, and there's 5 times 3 there and another 2, 17 pluses. So there are 2 little cross checks, charge checking and checking the number of each atom, when you get to these complicated examples. So we're going to do a little bit more of that with things that might be even less familiar, just to show you how it works. I'll see you when I've got the board ready. Okay, more complicated again than last time. Going to include cancellations. I'll show you what that is when we get there. Here's the 2 half equations, completely unfamiliar to people in your year 12, I would imagine, but perfectly valid. They come out of the chemistry book of half equations. It's not really a book, it's a couple of pages, but there we are. And there they are. The number of electrons is 4 there, 2 there. So this one here, this one with the S2O6 on, which you've never met before, it's called peroxodisulfate or peroxosulfate, is going to have to be doubled. So this here is the oxidation, this here is the reduction. You'd like to pause the video and check that. In fact, I think you should have been pausing the video and writing things down, maybe rewind it and do it all again. Anyway, here it is doubled. So now I can combine this one here with this one here, and here they are combined. Now it looks horrendously complicated because cancellations are going to take place. So when you look at this here, and my board isn't wide enough to get it all on, but I do encourage you not to put that water over there, because that water in the equation belongs on the product side, so don't write it like you're writing a sentence. It actually belongs over here. I still see people do that. Now when you look at this equation, there are 2 things that cancel out, and it's almost always water and hydrogen ions that you end up cancelling out. Occasionally it's OH minus ions, water, H pluses, but we're not going to do that. So here there are 4 hydrogens, here there are 8. So all of those will disappear and that 8 will become a 4. And you get the same thing going on with the waters. So 4 waters, 2 waters. So those 2 waters will knock out 2 of those waters. And there it is written in red with the cancellations removing 2 things. Now in this one it's removed hydrogen completely from the left hand side and it's removed water completely from the right hand side. And that will always happen. You will always remove hydrogen ions. If you're doing hydrogen ions and waters as the cancellation, you'll remove hydrogen ions completely from one side and water completely from the other side, and you'll still have some left over, some usually. Occasionally they'll completely disappear. Yeah, it makes it much simpler. So when you cancel out the 2 things that have appeared on both sides, because they will have to appear on both sides before you can cancel them out, so the hydrogen ions have to be on both sides. And you end up with that. I've put the state symbols back in because we shouldn't forget to do those. And the last thing is to do that 2 things that need checking. So you check the charges, and the charges there are 2 lots of 2 minus, 4 minus charge on that side, 4 lots of 2 minus, and 4 plus, 4 minus. And if you were to check all the different things, like there's 18 oxygens and various things, it all adds up. So that's that. Just got one further example, and then we are all done with this, and it's on to the follow-up questions. I'll see you in a moment when I've got the board ready. So here's our last pair to combine. I've called it cross multiplication. I'm probably calling it the wrong thing, but I consider it as cross multiplication. So here are the 2 half equations. This one's a thing that you need to get familiar with, called thiosulfate, S2O3 double minus, and it's turning itself into sulfur, so it's a reduction. This one's the oxidation of something we never use in school, but it's arsenic, turning into HASO2, which will be an arsenic acid of some kind. And there's the 2. It's not a straightforward multiply of one to make the other one, because there's a 4, there's a 3. So the only way to do that is that this one here has to go 4 times. Didn't leave much room for that. So, because 4 times 3 will be 12 electrons, and if you do 3 times 4 you get 12 electrons. So this one here has got to go times 3. So the reason I call it cross multiplication is 3 electrons gets multiplied by the 4 of the 4 electrons. So you multiply this one by that, and then this one gets multiplied by the 3 on this one to make the 12. So the 3 and the 4 get multiplied together. That's using the electron count. That then causes these 2 multiple half equations to appear, with the 3 multiplication on this one and the 4 multiplication on that one. You're going to struggle to keep up with me writing it all down. You're probably going to have to pause me, but maybe just listen and then rewind. So when you then combine them, it becomes terribly complicated with all of that, and I've yet again not got a wide enough board with the hydrogen ions popped off the end here. So there it is, combined, and then you get that cancellation taking place again. All of the hydrogen ions will disappear from one side, all of the waters will disappear from another. So looking at the waters, there are 8 waters there, there are 9 there, so the 8 will completely vanish and the 9 will just become a 1, which of course in chemistry means we don't write the number. And then when you look at the H+, there are 12 there, there are 18 there, so all those 12 will go from that side, and that 18 will come down to be a 6. And that's what we have there. That's the cancelled out version of that reaction. So we've come quite a long way from really straightforward half equations of just a metal and its ion and a few electrons. And here we've got this rather complicated looking thing, but the skills are there. We have the cancellation with the cross multiplication. Little checks at the end, like I always say. Look at the charge. The total charge on that side is -6, 6 plus, comes out as 0. And none of these are ionic in any way, so therefore 0 charge. And if you were to tot up how many oxygens, how many sulfurs, whatever, they'll all come out the same. You want to check that, you can check that. And that's it. Now there can be some follow-up questions. I have to be honest, I haven't quite finished writing them yet, so they will be not long after this video goes up. And, well, there we are. Thank you for watching, and hope you get on well with the follow-up questions, and I will see you again soon. Ta-da!